Hello and welcome to this training module about waste heat in district heating systems, especially about data center waste heat in the ReUseHeat project. My name is Oliver Rosebrock. I'm a technical consultant at Veolia Energie Deutschland, which is a part of the French enterprise Veolia, and we have a high experience in the district heating network business. If we look at the overall project, we have different potentials. We've had different demo sites, different ideas about how the project can look like. And in Braunschweig, or in English Brunswick, we had the possibility that a data center was constructed nearby a new residential area. And this gave us the possibility to be part of this project. If we look at the different potentials of different waste heat sources that are usually available in urban areas, we were talking about metro stations, we're talking about cooling processes in hospitals, sewage water, etc. These are all covered in other training modules. I want to talk to you about the data centers, which have a very huge impact right now, and with the increasing demand and with the expected increasing demand in electricity consumption for data centers, we've seen this over the last few years. We will have even more possibility to make waste heat or to see data centers also as a waste heat source. The literature research gave us about 48 terawatt hours per year of potential in the EU that are nearby district heating systems, and compared to the total heating demand of roughly 2,600 terawatt hours per year, which was a value from 2015 for the 28 EU states at that time, it can be a significant amount. So it is a part that should be covered, that we should make use of. If we think about data centers, we should think about them as waste heat sources. So because most of the electricity in the IT is basically in the end converted to heat. We've all seen this. Your laptop, your notebook gets warm over time, and so on. And usually the cooling system itself, just for the cooling of the IT installations, can make up to 40% of the total energy cost in data centers. That's a huge amount. So we have several problems. We have the rise of the energy cost. We have also the rise of the data center consumption, and we right now usually do not make any effort to recover this waste heat. But if we think about the waste heat, or let's say the cooling of the data center, and we take this heat as the waste heat, it absolutely makes sense to use it, because we have this task to cool down the data center, and we have probably, especially in urban areas, often the possibility to distribute the heat by district heating networks, and therefore it makes sense to use the waste heat. The advantages are simply we have a decarbonization for the district heating, because with the electricity we use, we cover different aspects, not only one task, but two. And we can also generate energy savings for the data center operators, and even also for the energy suppliers, for those who operate the district heating system. So from this general part, I now want to go over to Braunschweig to give you an impression of the city. It is a city located in Lower Saxony. It's the second largest city here. We have roughly 250,000 inhabitants, and we have a large focus here on science, and so universities are here, private research is here, and the energy supply of the city is covered by BS Energy, which belongs partly to Veolia, a large French company. And we're supplying the city with district heating and with natural gas. If we think about the district heating in Braunschweig, we're talking about district heating network that was installed already in 1924. As you can see here, Braunschweig is the English name for Braunschweig. Most of the heat is generated in CHP plants. So nearly everything of the heat demand that goes into the district heating network is covered by CHP plants. We have a total of roughly 250 kilometers of district heating grid in the core. So we have one large district heating network and several decentralized grids. Most of them have temperatures above 100 degrees C in the supply flow. So they were, as you can see, it was 1924, so old networks usually have these high temperatures. If we think about the market share of the heat generation in Braunschweig, it's roughly 1/2 of the heat generation in Braunschweig is covered by district heating. So it's a large, district heating is a large factor just in Braunschweig. And we're talking about 56,000 apartments right now, and additionally industrial and commercial customers as well as public buildings. And you can see on the right side, you can see that we have several different plants, all CHP covered, just two additional systems for peak loads. And this is the case right now. You will see why I'm talking about the status right now, because we make partly use of it also by when we talk about the data center energy concept. Why was it interesting to be part of the ReUseHeat project? So our main challenge actually is the decarbonization of the heat supply. Waste heat is one or can play an important role in the future heat supply. So because it is considered to be carbon neutral if we think about waste heat. So this is one possibility for us to decarbonize the heat supply. We have the possibility to have an experience gain in the heat pump use. So most of the CHP plants right now work without any heat pump installed yet. We will get experience in the waste heat use. So all the topics that are related to the technical part, the economical part, the relations to the partners, everything that is needed is covered because we have a project. It's not a theoretical one, but by being part of this project in Horizon 2020, we have the possibility to really have practice project and therefore gain an experience gain in all of these parts. Then, of course, we have good effects in terms of attractivity, marketing for customers and shareholders. So we can say we have now subgrid, where we have huge part of waste heat included. So we have very decarbonized part of the district heating. So all house owners connected to the grid make use of the advantage of this low emission heat. So this belongs also to the next point, the meeting future requirements, because it is said that the heat supply must be decarbonized, and therefore we are here now able to meet the future requirements. Another nice part by using the waste heat is that we make use of regional heat sources. So we do not have to we are less dependent from external heat sources like coal, natural gas, or heating oil. These fuels which are mostly not from Germany, or not mined here in Germany directly. Now directly to the project. You've seen this map here before on the right side. So we're in the southeastern part of Braunschweig. There was a new district that was built over the last years, which had a residential property here on the bottom side. And then we have the data center here, and additionally also a commercial area. In this place here, we have the energy generation. The energy generation is directly beside the data center property. We're talking about a residential area of 400 accommodation units. It's roughly 21 hectares. And we have, given that the existing high temperature district heating network is here, already here nearby this new area that was constructed and designed. This is something you can also see here on the right side. So the existing network is available too, but we also have the data center here. If we look on this property, it was an old military site, which wasn't in use for years. And this is how it looked like in the very beginning. So in January of 2017, 5 years ago, it was just, nowadays you might say it's nearly a lost place. So it wasn't in use anymore. And therefore, it was developed for housing purposes. If we think about the energy concept here right now in this building, or in this district, as I said, we have our customers, the residential area, also the commercial area. We have the data center, and the data center is now covered up with a heat recovery system, which is actually just a heat exchanger, and the heat exchanger is connected with a heat pump. And the heat pump then transfers the heat from this low temperature level, which is roughly 25 degrees C here. So data center is cooled down to 25, or the cooling system of the data center has a temperature of 25 degrees C. And by heat pump, this temperature level is increased to 70 degrees C, which is the supply flow temperature of the district heating network for this new area. This new area is also indirectly connected with the existing district heating network. This is why I mentioned this before. So in terms that we do not have enough heat recovery or waste heat available, in terms that we have this huge shift between summer demand and winter demand. So we use the existing district heating network as the peak load coverage for this subgrid. So a new subgrid was installed, connected, or the heat generated port is first of all by the heat pump that uses the waste heat from the data center. And we also have, for the peak load coverage, the connection to the existing district heating network with a high temperature. So if we think about the dimensioning of this heat pump here, it was said that it makes sense to cover the base load, and for this it makes sense to have roughly 250 kilowatt hours of heat recovery, and then a heat pump that delivers 380 kilowatts in that case. So two good sources, the waste heat as generated ports and the CHP district heating network as a coverage. If we talk about how much area is supplied, we're talking about 48,000 square meters. We have this low temperature network here, has roughly 2.8 kilometers in length. We have a 600 or nearly 700 meter length of connection to the district heating network sites. You've seen this. It was in the south of the new district. There was the end of the existing district heating network, while the energy generation was besides right beside the data center, and therefore the connection from the district heating network towards the new energy plant needed to be quite long. We expect to get something like 2,300 megawatt hours per year out of the waste heat. We expect an SPF, so efficiency of the heat pump, of 3.6. And in the end, we hopefully can reduce the CO2 emissions by up to 300 tons per year, which is a quite good number. So a reduction of 130 grams per kilowatt hour of reduction. So a very low value in the end. How does it work in detail? It's a bit technical right now. I'm sorry for that. So as I already said, the base load is covered by the waste heat combined with the heat pump. The peak load is covered by the existing high temperature network, which has up to 130 degrees in summer. The temperatures in the low temperature network are 70 degrees C in the supply flow and 40 in the return flow. There's a small mistake on the side. This is return flow and this is also return flow. And the temperatures in the cooling cycles of the data center are 25 and 80. So we get 25 degrees C from the cooling system. We cool it down to 18 degrees C. And then we increase the temperature to 70 degrees C and put it into the supply flow. This is more or less the idea behind the system by using the heat pump. We had this requirement of 70 degrees C in the supply flow. So, or this still quite high temperature of 70 degrees C in the supply flow is caused by the hygienic requirements. So we have the topic of Legionella, which leads us to have at least 60 degrees C in the heating systems to avoid Legionella problematic. And therefore, the supply flow temperature needs to be higher than this. And 70 degrees was the value chosen here. This was especially because we wanted also to deliver domestic hot water, not only space heating. If we think about how it is done in detail, so this is more or less a very simple schematic. So we have the data center operator. The data center operator has a heat exchanger, and the heat exchanger is connected with the evaporator of the heat pump. Then we have the heat storage. Then we have the high temperature district heating network, which has the heat exchanger with the heat storage. And we have the low temperature district heating network covered from the heat storage inside this plant. You can see, actually, this is the only connection to the data center. So this is where, let's say, the heat comes from, where this cycle is included. And there's just one connection between us as the energy supplier and the data center operator. So the heat pump can give a signal to a pump on the data center operator side to start volume flow that goes over the heat exchanger. So there's a signal on or off, start operation. Please start the operation of waste heat recovery, and then everything is fine. And this is also linked to the heating demand. And then additionally, for the additional cooling demand, the data center has an additional cooling machine installed. But this is how it looks like. So it's on the technical side, a very, very short or very small connection needed between all the facilities that belong to the data center operator and the facilities that belong to us as the energy supplier. If we think about the system even a bit more, especially the heat pump itself. The heat pump itself is not only engine of choice to increase the temperature level. But for this, specific cooling fluid is needed. If you think about the old the times in the 80s where we had these HFCs inside the fridges, etc., we knew afterwards that these were harmful for the climate. So one additional factor in terms of heat pump systems is to think about the cooling fluid, the working fluid inside the heat pump. For this, it is we defined several requirements for the working fluid. So we said if there's a leakage and for whatever reason inside the machine, we want that the working fluid is non-toxic. We want that it is non-flammable, and we want to have a low global warming potential. So if we think about the global warming potential, it is, let's say, a reference or a ratio of how harmful it is compared to CO2 that is released to the ambient air. And then if you go on the market, you have the choice between artificial working fluids and natural working fluids. And one natural working fluid is CO2 itself, which is quite new technology in terms of heat pumps and cooling machines. And we chose this model of this heat pump model displayed here, which uses CO2 as a working fluid. Additionally, we installed two different compressors inside the heat pump, one on-off and one with an inverter, so that we are able to cover also partial loads of the waste heat system. This is simply for topics which I will talk later a bit more on. But we have this rise of the installed IT capacity, so we needed to be able to start operation as soon as possible to install even partial load possibilities to use the waste heat. I want to give you some more impression of how it looked like and how the development on the site was. So you've seen this before, the photos from January 2017, and nearly 2 years later, you can see already the data system was constructed here. It's on the left, here on the left, and you can also it was seen that all the first housing areas were constructed. So the operation started and went on, and in March 2019, the heat pump itself was already delivered and installed. You can see it here. So it was delivered here with a crane and then installed inside the heating plant, which, as I said, is directly located beside the data center itself. Then this is what you can see here on the bottom right. So this one is the heating plant here on the left, and this one on the right here is the data center. So it is nearby, so small piping length to make use of the waste heat. Then you can also see the housing area increased. So more buildings were built. Some were already finished. People already living there. And so in the first place, until the heat pump was installed, only the high temperature district heating was covering the heat here in the system. But right now, we are able to cover also partly the heating demand by the waste heat. Then, the heat pump was commissioned, but only in 2021, in the end of 2021, because there were several problems with the availability of the waste heat. So as I said, we installed two different compressors, one with inverter, one on-off compressor, but unfortunately, there were still problems with the availability of waste heat, so we were not sure whether it is possible to cover enough of waste heat power so that the heat pump itself can run permanently. So we had, let's say, 30% partial load that could be covered from the design value of the 250. And it was not sure whether there will be really 80 kilowatts delivered. Fortunately, we now see it is possible, and the heat pump is running. So this was a success at the end of last year, and we're happy that the heat pump is running now. If you talk about the relation between the energy supplier and the data center operator, which is a huge factor in such a project. First of all, it is, as I already said, the data center operator will save money for the cooling because he will save electricity, the electricity we need for the heat pump, and also, therefore, he will save CO2 costs. And additionally, he will meet can meet efficiency requirements that are now more and more defined by the EU for data centers. So this means, as boundary, that we can think about, well, probably the energy supplier could be paid for supplying cold because of the savings on the data center side. This is just one possibility. In our case, we have had additional things that were discussed, and one very important point is obligations. So in our case, we agreed, both parties agreed on no obligations at all. So it is not that we are obligated to provide cold to the data center because they have another facility. On the other hand, they are not have no obligations to deliver the heat to the heat pump. So if there's for whatever reason problems on our side or on the data center side, there's no obligation and no additional cost, no contractual fines or whatever if there's no delivery or providing on our side or on the data center side. As I said, only the one pump on the data center is controlled by the heat system, so we have very few interferences between both systems, which is quite a good thing. And we think in the future, so for let's say, projects in the future, maybe the waste heat will be a product with its own market risk. Hopefully for us, the cold delivery will be paid, but maybe also if heat pump waste heat will be a product itself, it can also be that the heat delivery is paid, so that those who have the waste heat available will be paid for it. But I personally think that more or less the providing of the cold will be a very important part for the business model of the waste heat use. If we think about the challenges for data center waste heat use, we have, first of all, we have some challenges on the law side, on the ordinance and the funding. So, of course, the funding possibilities changed over time. Maybe more attractive ones are available, but in the end, the goal should be that no funding at all is needed to have good business case for waste heat use. Then, as I already said, the contract between the data center operator and the energy supplier is just a challenge. You have to find find keys how to deal with these obligations regarding the delivery. On the economic part, if we think about the system, the main fuel, let's say fuel that is needed to make use of the waste heat is electricity. So of course, the electricity prices and uncertainties in the electricity prices are an important factor. So if we have right now, if we have a very large shift between or very different development of, let's say, prices for natural gas or whatever other fuel may be used compared to electricity prices, we have a risk or a challenge that needs to be covered here. We have higher investment compared to the facilities that are used or that could be used comparatively. We have higher risk compared to environmental heat sources. So if we think about the use of the heat pump and we think about environmental heat sources, so for example, geothermal or even the outside air, it could be here that the availability of waste heat is not given all the time, while a geothermal heat, for example, would be there. And so your kind of security of planning is an important point. And of course, for this model here, it is important that we have a location of the data center that is nearby district heating network. So the data center should be located nearby a district heating network. It's a small mistake on the slide. And maybe we also have competition with existing district heating networks that have still capacity to supply more customers. So these are very important factors that need to be considered if we think about data center waste heat use. But especially the location is one very important point. So if you need, let's say, 500 meters, 1 kilometer, or even more tubing just to connect the data center to a existing district heating network, probably this will not be economically feasible. This is a very important point. If you think about the risk, it's all, of course, the main risk for us, and what we figured out was the availability of waste heat. So in our case, we had delay. There was a delay in the data center commissioning. Let's say it was mainly related to COVID. So this means they had fewer installation than expected, and the installation took a longer time. And as I said, we need a certain base load of waste heat available, and this was not given for a long period of time. Therefore, we couldn't start operating. So this is especially a risk in the very early stages of the waste heat use. And then, of course, just another point, which is, I think, if we talk about waste heat use, especially industrial-related waste heat use, we have a risk in the future necessities. So maybe we'll have a change in the data center operator strategy. Maybe the data center will close down, or lower than expected installations will be there permanently, or maybe there's a technological change so that less waste heat, less energy is consumed, so less waste heat is available in the data center. Things like that need to be covered if you think about doing a project like this. So waste heat is just different from a classic heat generation. So we have kind of a divergence of the supply and demand that can occur. But for this, you have things like storages. So there are technical solutions for this, but the main risk is, to me, the availability of waste heat. On the other hand, we have very good opportunities. So as I said, we have a very high potential for decarbonization of the heat supply, which is, as I said, electricity prices are a main factor. Heat can be a problem, but on the other hand, it is way more easy to generate green electricity in a very scalable level compared to, let's say, green heat out of other fuels. So by using a heat pump that is covered by electricity, it is quite easy to decarbonize the heat supply with the use of green electricity. We have many different heat sources in urban areas and cities available: industry, the sewage water, the data centers, and several other things. Maybe rivers, which more or less environmental heat, but things like that. And you always should think about where are possible waste heat sources available. But on the other hand, as I said, the location should be nearby. It should be clear what prerequisites you need for the decentralized feed-in of heat. So if there's already a network available and you have, let's say, a centralized generation, one important thing is to think about the hydraulics, the prices, the pricing models, etc. But this is just one thing that is, let's say, a property of the waste heat itself. Overall, we think that in a new district heating system and in renovation of existing district heating networks, waste heat can play a major role. But as I said, you have to consider all the different topics. So something like we did here, like SWOT analysis, this is a very important point. And now I want to thank you for your attention. And if you have questions, please feel free to contact me. Thank you.